Hi, my name is Ashton Woods. I'm a geologist with the United States Geological Survey at the Earthquake Science Center in Menlo Park, California. I am presenting today on climate change impacts on natural hazard events. This is part one of a two-part series, and I am excited to get started. Please give me a moment to share my screen, and we will continue on with the lecture. Thank you. Lecture 14, Climate and Hazards, Part 1. The most common misconception on climate change is that it's synonymous with global warming. Global warming is just one variable, however. Climate change is defined as atmospheric and surface changes over time that occur across the globe. Variables of climate change are rising temperatures, ocean acidification, desertification, and the increase of natural disaster frequency that can cause damage to the environment. These variables could be influenced by anthropogenic consequences, but it is important to understand that climate variations are not uncommon throughout Earth's history. Review of the paleoclimate during the Holocene reveals similarities in conditions that we experience with climate change impact and is evidence that climate variations are a normal Earth process. So indeed, we could blame anthropogenic exchange as a contributing factor to rising temperatures and sea surface changes, yet the historical trends revealed that our climate is reaching similar conditions to that of the Holocene climatic optimum that occurred 9,000 to 5,000 years ago. This is because our planet has continuous intervals of mass cooling, global glaciation, and mass heating that we can trace from ice cores and from in-field investigation of rock facies. So why is modern-day climate science necessary if these variations are a naturally occurring trend throughout Earth's history? By understanding current climate change conditions, the global communities are capable of increasing disaster resiliency, which can improve the design of future technologies that monitor environmental and atmospheric anomalies as they occur. So let's explore recent data. The chart on global averages and temperature on sea level rise between 1995 to 2020 is progressively increasing. Current projections following on a business as usual schedule of existing climate conditions indicate that by 2100, Earth will be in the warm house state that was last experienced during the Eocene epoch, also known as the greenhouse Earth state, when glaciers were absent. Our current climate is still within the ice house Earth state from the last ice age. Indicators on the effects of rising temperatures and sea level include increase in storm intensity, unpredictable weather, extended droughts resulting in crop failure, and environmental pollutants causing environmental disease to emerge at an alarming rate. During part one of this lecture, we will investigate into the variables of atmospheric changes and how natural hazards contribute to the impact made by these variables during disaster events. Mechanisms on climate change, dealing with atmospheric conditions. Here we'll take a look at this diagram that will explain how different types of greenhouse gases contribute to global cooling, increased UVB, and ozone destruction. The gray circle labeled number 2 on the left-hand side deals with halogen gases. Most of these are introduced into the atmosphere through anthropogenic action, but can also occur naturally. These halogens can be bromomethane, resulting from pesticide usage and entering into the atmosphere during crop burning. It also includes chlorofluorocarbons that normally are introduced into the atmosphere through aerosols. The green circle on the right-hand side labeled number 3 deals with the primary natural gases that are released into the atmosphere during normal activity in the Earth's environment. These are the greenhouse gases. Fracking, fires, and energy sources that rely on fossil fuels are human interactions that increase the exposure of GHGs into the atmosphere. These involve methane, CO2 or carbon dioxide, nitrogen dioxide, and in some rare cases, hydrofluorocarbons, which are known for ozone depletion. The interaction of hydrofluorocarbons with chlorofluorocarbons can come together into the atmosphere to form hydrochlorofluorocarbons, particularly dangerous as they are extremely difficult to remove from the air and surface sediments. Hydrochlorofluorocarbons are known for causing severe ozone depletion that cause unpredictable variations of wet and dry season patterns in the northern and southern hemispheres. We'll look into a closer perspective of ozone gases in the ozone layer. This graphic is a daily max zone for July 27th of 2020, where the daily max represents an 8-hour interval of observational data collected on atmospheric changes dealing with the ozone layer. The colored scale at the bottom of the image is represented in parts per 100 million, or pphm. The safe zone is normally The safe zone is normally indicated as 0.10 parts per million over the daily max, and as we can see, the highlighted sections in blue have converted to 0.01 parts per million. The blue regions are far below the safe zone requirement set by the global standards, while the green areas are represented as 0.04 parts per million, and the red regions are nearing 0.07 parts per million, nearing the maximum safety level of O3, or ozone gases. This is the ozone total column diagram showing the ozone thickness recorded at the time of July 29th to 30th from, again, my apologies, recorded at the time of July 29th to the 30th of 2020. At the bottom of the scale, as measured in Dobson units, represents the thickness of the ozone layer. 300 is the globally accepted average in Dobson units for how thick the ozone layer should be. Anything below 300 is susceptible to tearing or the creation of a hole within the ozone layer, thus allowing for excess cooling to happen in such areas. Cooling can worsen when there is a hole in the ozone layer and nitrogen dioxide levels have spiked. The daily max is again another 8-hour interval of observational data dealing with the atmospheric changes of nitrogen dioxide on July 27th of 2020, calculating for the atmospheric nitrogen dioxide limit. We look into parts per billion for this graphic. The green to yellow regions appearing on this map may seem concerning. However, the toxicity limit for nitrogen dioxide over an 8-hour interval is 150 parts per billion, so these areas are still within safe levels of NO2. The flare of red reaching into the 140 to 160 range for parts per billion in Greenland is of more concern, as 0.1 parts per million or 100 parts per billion is known to cause respiratory complications such as asthma and emphysema, and can eventually cause death to occur if exposed to these levels of nitrogen dioxide within a week of exposure. High NO2 in the atmosphere, when there is vulnerability within the ozone layer, causes storms to happen erratically and can increase storm intensity when CO2 and methane levels are so high. Another mechanism that helps contribute to the greenhouse gases in the atmosphere is the deforestation of tropical swamplands in Indonesia. The aerial image that we see here is a palm tree plantation located on an unspecified swampland area within the Kalimantan region of the island of Borneo. On the left-hand side, we see that there are very limited to no trees in the brown and tan areas on the image, and that there's evidence of desertification beginning to occur. The map that we're currently viewing covers CO2 emissions from peatland degradation, originally designed in 2009, but updated the FIT projections for 2017. Here we can see that Indonesia contributed that year of up to 200 million tons of CO2 emissions from peatland burning and peatland degradation. Here we see a series of diagrams. On the bottom is a healthy peatland showing that there is enough soil saturation to prevent carbon deposits buried beneath the surface from being released into the air. Without the interference of oxygen from the air, the vegetation in the peatland is responsible for taking in CO2, leaving the carbon trap. The above diagram shows what happens when the peatlands start to become drained. Draining peatlands can occur during irrigation efforts for agricultural crops or during prolonged drought conditions. So water leaves the peatlands become more susceptible to developing methane and carbon sinks, where the oxygen is able to enter into the soil, increasing rates of decomposition of organic material and allowing for a higher concentration of CO2 emissions to escape. The top diagram for this page shows consequences of what happens when fire is introduced into a drained peatland area. Most fires happen because there isn't enough moisture in the soil to protect the vegetation from dying off, and the vegetation becomes extremely dry during the drought seasons, and different types of atmospheric changes can ignite the surface. However, the majority of the fires that are set in Indonesia that contribute to CO2 release and methane release from peatlands into the atmosphere are due to slash and burn agriculture. Once the fire is burned on the surface, it begins to release CO2 and methane at exponential levels. Oxygen within the soil mixed with the carbon deposits are perfect for fueling fires that can burn anywhere between several days to weeks and even months after the initial fire has been set in the peatland area. To see this, we have a diagram on the right-hand side. There's a tropical swamp. The fire has already set ablaze to the swampland where the peat has experienced drainage from the village across from the man-made river channel in this diagram. The peat deposits beneath are starting to ignite, so when the fire dies on the surface of the swamp, the carbon and oxygen trapped in the underlying peat deposits are still consistently burning. Fire is able to travel through the peat deposits beneath the village a month after the initial fire. The village is yet to experience issues, yet outlets on the surface or damage to the soil profile can allow oxygen to fuel the fire up and out of the ground, eventually catching the village on fire. Damages caused by peatland fires with the increase of greenhouse gases into the affected area damage the equilibrium of humidity and temperature within the area. Droughts can last longer in these areas, causing soil surface changes that create ideal conditions for landslide and liquefaction to occur during seismic activity, regardless of the size and magnitude. Here we see a map from 2018 showing CO2 flux in the sediment CO2. The majority of the CO2 that is being released surprisingly isn't happening in Borneo, but is happening mostly in Sumatra and the urbanized areas of Java, along with the trailing islands following Java. The large circle represents CO2 flux of over 2,500 tons per day being released, while the green, yellow, orange, and red colors for the lines and circle represent the percentage of CO2 fluxes that are being released from the sediment during periods of surface change, soil disturbance, or peatland exposure. Peatland fires can end up burning large amounts of agricultural crops, especially since most of the peatlands are being removed for oil palm plantations. The fertilizers and pesticides that go into the palm plantations and other agricultural crops are responsible for the release of concentrated levels of formaldehyde. Formaldehyde, cyanide, ammonia, and carbon monoxide are introduced as air pollutants following crop fires, making a very toxic situation for the surrounding environment. The formaldehyde peak that we see at the end of 2019 to 2020 is representative of the fires that broke out across Indonesia during September 2019 to the beginning of the year of 2020. Formaldehyde, however, doesn't last very long in the atmosphere, so even though there were a majority of fires that happened in September of 2019 to the beginning of 2020, atmospheric conditions for the summer of 2020 reveals limited remnants of formaldehyde still present in the atmosphere, as we see here. The reason for this is because formaldehyde levels in the atmosphere are degraded by exposure to ultraviolet radiation, particularly UVB. This image is the Solar Noon Index for July 27, 2020, showing that there are extremely high levels of UV radiation over the main islands of Indonesia. On the scale below, 0 represents a very low susceptibility to negative implications of UV light, whereas 16 represents a high dangerous level of UV radiation that would normally cause severe damage, responsible for not only environmental but human-based diseases that occur from overexposure to solar radiation. I would now like to take the time to look into the emissions from volcanic eruptions and how these emissions help to reduce solar radiation exposure over Indonesia, but add into atmospheric high levels of sulfur dioxide and act as a mechanism for climate change. Here we see footage from the Himawari satellite of the Anak Krakatoa eruption in the Sunda Strait on December 22nd of 2018. The footage is showing how the atmosphere is igniting from the mixing of sulfur dioxide and other harmful gases with extreme temperature output, thus disrupting the equilibrium of gases in the atmosphere. This footage is presented in clean infrared window and band 13 for the Himawari satellite. Additional footage from the Himawari satellite is seen here, but through bands 3 of red visible imaging showing the different cloud formations that occurred after these gases were released into the atmosphere, and how the atmospheric changes caused significant meteorological events to occur within several days following the eruption. This chart shows rises and peaks that correlate with volcanic eruptions that happen across 4 main islands of Indonesia with immediate risk of volcanic disturbances and disaster events. We see that there is a sharp increase and then sudden decline in the data. This is representative of times of eruption when significant amounts of sulfur dioxide were released into the atmosphere over Indonesia. We see this also being relatively high at the end of 2019 to the beginning of 2020, which is not entirely surprising since this is when an increase of volcanic activity along the Ring of Fire during the beginning of the year suddenly dropped off in frequency of eruption, which you could see near the end of the chart during the summer of 2020. We see this decline in sulfur dioxide in the summer for July 29th to July 30th of 2020 over Indonesia, as the Dobson units of sulfur dioxide in total column is relatively low, if not almost zero, over the main islands. Soil dioxide is removed from the atmosphere through dissolution of water bodies and through absorption into well-drained soils. So coastal and brackish wetland areas tend to be primarily natural resources of removing SO2 from the atmosphere following volcanic events, which allows for acidification to occur. The diagram explores further into acidification of marine environments. The CO2 is able to filter in and out of the ocean into the atmosphere, creating a harmony within the healthy marine biome along the coastline. However, as more CO2 with the environmental pollutants and greenhouse gases are introduced into the atmosphere over time, these gases become cycled through marine waters, and the ocean produces more quantities of carbonic acid and free hydrogen ions. The oceans become more acidic, damaging natural coastal barriers such as coral reefs and mangrove forests that help to protect the coastline from tsunamigenic energy and high tide activity. Here on the right, we see an image showing daily averages collected over a 10-year period between 2010 and 2020, representing exposure of natural barriers to acidification and an increase in soil surface temperature, marked in Kelvin. The combination of these conditions are also responsible for the increase in storm intensity within the past 5 years, particularly during typhoon events. The following map shows the percentage of protected marine environments for Indonesia for 2018 to 2020. The darker purple areas are not very well protected by government authorities or global initiatives, so the cities that rely on the coastlines in these areas are often left to their own devices whenever major storms or different types of disasters happen within the area. The darker to lighter green colors show a higher percentage of protection, which allow for flood resiliency and stabilization of the coastline during typhoon, tsunami, and high wave, high tidal events. Here the same map is grayscaled, highlighting the different areas of high susceptibility for flood impact during flood-related disasters, and for areas in Indonesia that are considered flood resilient by comparison. Of the flood resilient areas, we see that the trailing islands behind Java, including Timor and western and eastern Nusa Tenggara, along with the West Papua, are considered to be highly resilient with very little flood impact during disasters along the coastline. Oh, my apologies. However, high flood risk areas that are presented in red are located on the coastlines of Java and Sumatra facing the Indian Ocean. The influence of urbanization as well as natural occurrence of seismic activity can present challenges when it comes to protecting these areas from tsunami and high tide, high wave events, as the existence of natural barriers is extremely limited. These areas are also inclined to unpredictable meteorological conditions that can influence ocean anomalies such as meteotsunamis to occur. Meteotsunamis or meteorological tsunamis are influenced by gravitational forces and changes in barometric pressure in the atmosphere. All that is required for meteotsunamis to result in coastal flooding is a high tide event to be influenced by these additional forces. It is very difficult to predict when these hazards can develop into disaster events, but they are normally responsible for the majority of flood-related disasters that happen following volcanic and seismic activity, where initial tsunamigenic wave generation is not present. However, this does not mean that meteotsunamis cannot make tsunami activity worse, and we will go on to an example of how this happened in a Anak Krakatoa eruption and tsunamigenic event of 2018. But first, a simulation. Following is a simulation that will go into the deeper mechanics dealing with meteotsunami generation and how it affects the coastal environment and coastal zones.
Phase 1: Atmospheric disturbance and the oceanic response. In a specific, fairly well-defined synoptic meteorological situation, internal atmospheric waves are generated, generally moving from southeast to northwest at a speed that may reach around 100 kilometers an hour. Some of these waves can give rise to convective storm systems, and there may be violent discharges from the upper atmosphere. At surface level, all this causes rapid and rhythmic oscillations in atmospheric pressure, accompanied or sometimes replaced by isolated pressure jumps. Such oscillations or pressure jumps may reach the order of several hectopascals or millibars, causing a response on the free surface of the oceans in the form of long waves, of several centimeters in amplitude. In the open sea, in deep waters, long ocean waves are propagated at some 600 kilometers an hour, decoupled from the atmospheric forcing that creates them. Phase 2: Atmospheric oceanic coupling and amplification. When ocean waves reach the Menorca Channel, which is approximately 80 meters deep, they slow to approximately 100 kilometers an hour, and this may cause coupling with the atmospheric disturbance, wave or pressure jump. As long as this coupling lasts, there is an efficient energy transfer, and ocean waves are rapidly amplified, reaching some tens of centimeters in amplitude. Phase 3: Coupling in Ciutadella Port. Due to the peculiarly long and narrow layout of the port of Ciutadella, incoming ocean waves with periods of the same order of magnitude and comparable may be amplified by resonance, causing the waves to be amplified up to 10-fold or more, even on occasion reaching 4 meters in amplitude. In almost all meteotsunamis, including both more intense and ordinary events, there is usually one major oscillation, causing the port to drain and fill up, followed or preceded by a series of secondary oscillations of lower amplitude, which may last for several hours.
The Anak Krakatoa eruption in Sunda Strait at the end of 2018 resulted in an underwater landslide that caused tsunami conditions to generate that impacted the surrounding coastal cities. 14,000 individuals were affected by these waves and 426 people died from inundation-related events. There was an early warning for high tides within the area prior to the marine landslide event, where the waves had reached up to 2 meters along the coastline. It is believed that the influence of gravitational forces from the close proximity of the moon to the Earth influenced a meteotsunami to generate during the high tide warning, fueling the amplification of tsunami generation that would occur later. On the map, we can see the high tide warning areas highlighted in the red circle. For the cities along the coastline of Western Java and southern Sumatra, we can see that the wave generation patterns highlighted as gray fans throughout the map. It is by the influence of the high tides and the meteotsunami interaction with tsunamigenic wave amplification following the marine landslide that allowed for different variations of data to emerge and a lack of evacuation warnings to be issued following the Anak Krakatoa eruption of 2018. It is the influence of these atmospheric and meteorological interferences that generate significant disaster level events and the presence of climate change as a primary effect on storm intensity and disaster vulnerability. Climate change should be considered in hazard mitigation process when constructing disaster risk reduction, response, and relief policies. Comparative data between nations allows for global initiatives to produce vulnerability and resiliency ratings that explore into the current mitigation tactics that address climate impact as a key motivator for disaster frequency. In this bubble graph, I have selected 2 additional countries alongside Indonesia to compare vulnerability and resiliency rating. Here we will look at Indonesia, Japan, and Samoa. The circles are representative of each country's GDP in relation to building disaster resiliency and diminishing vulnerability to climate change impact, while the colors are on the top right. My apologies. When the colors are as the top right key shows the level of sufficiency to insufficiency of compliance with the Paris Climate Agreement. Japan has a larger GDP and is considered, here, as seen here, and is considered partially sufficient. However, as we look on the X and Y axis, we see that Japan contributes to a large amount of CO2 emissions in comparison to Indonesia. Indonesia, located here, is lacking climate disaster initiatives and compliance with the Paris Climate Agreement, so is therefore considered highly insufficient, with limited GDP for combating against vulnerability of climate change impact that contribute to Indonesia's placement within the bubble chart. And over on the left-hand side, we have Samoa, which does not produce much CO2 emissions and yet is highly insufficient and is least prepared for combating climate change impacts in relation to natural disaster generation and frequency. We see this further by investigating into global ranking scores. Indonesia ranks numbers 97 on the INDIGAIN Country Index, an index that summarizes the nation's vulnerability to climate change impact and disaster-related events. It takes into consideration vulnerability, readiness, and resiliency. The ranking is 1 out of 170 different countries, where the lower the ranking a country is towards 1, the more sufficient they are preparing against climate change impacts and reducing vulnerability and raising resiliency in accordance with global initiatives. In the year of 1995, we see that Indonesia once had a score of 121. And in 2018, the score has decreased to 97. This is significant improvement, yet the vulnerability and readiness rating are still relatively low in comparison to other countries, as seen here. In order for the index ranking to move towards a lower value, Indonesia must take into consideration new initiatives for hazard mitigation that include climate change impact as a source of disaster generation and atmospheric anomalies in relation to disaster frequency. Japan is ranked number 15 on the same INDIGAIN index. It is almost ironic that the ranking is so low and that their readiness to combat against climate change impact is so high compared to that of Indonesia, as Japan is still considered as a main CO2 emitter for the globe. And then we have Samoa, which is only 1 rank behind Indonesia. Samoa has the lowest CO2 emissions, and yet we see that from 1997 to 2018, their score has been increasing higher in rank, which is a bad thing. The increase is because Samoa has dedicated its resources into the utilization of fossil fuels to help increase infrastructure production and urbanization efforts beginning in 2015 and moving towards 2030. Because they are introducing more CO2 into their surrounding environment, their vulnerability has been steadily increasing. Samoa has been projected to experience more storm intensity and wave generation in the next 5 years due to the introduction of greenhouse gases in the local atmosphere. This will conclude part 1 of climate change impacts on natural hazards. This concludes part 1 of climate change impacts on natural hazards. I hope that you all were able to retain all of the information that was in this presentation. I promise that the second presentation is shorter, and I look forward to presenting part 2 with you all. And as always, please remember to remain safe during the COVID-19 pandemic, wear your mask, social distance, and make sure that you are keeping in touch with your needs and your health, because we need you in the future to continue on with your science and your contributions to the scientific world. Thank you. and I look forward to the next presentation.